My name is Xinwei Du, and I'm from the Beijing Normal University, Hong Kong Baptist University, United International College. And today, my topic is called the ML and the map estimation of frequency offset and linear phase noise in coherent optical communications. And I will introduce the contents in the following steps. So firstly, we will start from a brief introduction to the motivation of our research. And then we will look at the maximum likelihood estimation of the frequency offset and the constant phase offset, and the maximum a posterior estimation of the linear phase noise vector theta. And then we will further develop a amps power carrier phase estimation approach to improve the carrier recovery performance. And then we will derive the Cramér lower bounds to evaluate the estimation performance of the proposed algorithms. And finally, we will look at some simulation results and give a brief discussion and a conclusion to today's presentation. So firstly, with the explosive growth of the network traffic data, the users now have higher demand for the data transmission speed and data transmission capacity. So a possible solution to this problem is to utilize the high order modulation formats. But in this case, the system may be more sensitive to the effect of the frequency offset and the effect of the phase noise. So the frequency offset is mainly caused by the frequency or the wavelength difference between the transmitter laser and the local oscillator, while the phase noise is caused by the non-zero laser lengths, which will cause the phase rotation of the constellations. So to deal with these two distortions, we mainly consider this kind of signal model. So this is the received signal, this is the transmitted signal, and this Xi represents for our frequency offset normalized by the sample rate, and this phi represents for the constant phase offset, and this theta of k is the linear phase noise, which is modeled as the Wiener process in this case. And this n of k represents for the complex additive white Gaussian noise with the mean of 0 and the variance equal to n0. So here we let the first n symbols to be the pilot symbols, and these pilot symbols are unmodulated with the amplitude equal to a. So this received pilot symbols can be expressed in this form. And we can further express it in the polar coordinates in this form. And if we consider the angle of the received signals, we can express it as the vector matrix form. And here this theta is a vector that contains all the observations of the phase noise. Well, this epsilon is called the additive observation phase noise, which is mainly caused by this complex additive white Gaussian noise. And this epsilon is usually taken-off distributed. But when the SNR is high, this epsilon can be approximated to the normal distribution with mean 0 and a covariance matrix sigma epsilon can be expressed in this form. So, and similarly, this theta is also normally distributed with mean 0, and the covariance matrix can be expressed in this form. So based on this relationship, the estimate of this Xi, phi, and theta actually should be the one which can maximize this joint density function. And based on the Bayes' theorem, we can obtain this joint density function can be expressed as the production between the two density functions. And by looking at this density function, we can observe that the ML estimate of this Xi and phi can be obtained by maximizing this likelihood function. So since we have this relationship, we can see that the angle of R should be normally distributed with mean value equal to this term. And the covariance matrix is just the covariance of theta plus the covariance of epsilon because they are statistically independent. So based on this distribution, we can write out the corresponding likelihood function, and the ML estimate of Xi and phi should satisfy the first order necessary condition that their partial derivatives should be both equal to 0. And then by solving these two equations, we can actually calculate the closed form expression of this frequency offset and the carrier phase offset estimates. Okay, so then based on this epsilon and phi, we can consider this density function that the estimate of this theta should be the one which can maximize this density function. And by applying the Bayes' theorem again, this density is actually proportional to the production between these two densities. So finding the value of theta that maximizes this density should be equivalent to find the value of theta that can maximize the production of these two densities. And since theta is independent from Xi and phi, and by writing out the details about these two density functions, we can see that actually by maximizing the production of these two densities is equivalent to minimize this equation or to minimize this function. So by considering the first order necessary condition, by taking the derivative of this function with respect to theta and let it equal to the vector 0, we then can obtain the closed form expression of this maximum a posterior estimate of this linear phase noise vector, conditional on Xi and phi. So by putting this, by replacing this Xi and phi, by utilizing their ML estimate obtained in this page, we can finally obtain the map estimate of this theta or of this linear phase noise. But be careful, this linear phase noise is only obtained on the parallel symbols. For those unknown transmitted symbols, we need to still apply some other phase estimators to make sure that the carrier recovery on the unknown transmitted symbols are accurate. So that is why in the next step, we further derive the Am's power carrier phase estimator. And here we assume that our YT is the received signal after the compensation of the frequency offset and the constant phase offset by utilizing the previous ML estimates. And we assume that the phase noise varies slowly so that it can be regarded as a constant phase within the time window from K minus L to K plus L. And then by performing the Am's power of this received signal, compensated received signal, and we found that the angle of this signal actually have this relationship. And since recall that for this additive observation phase noise, it has the mean, it can be approximated as Gaussian distributed when the SNR is high. Then we can obtain the joint density function of all the observations inside this window, which is actually the likelihood function. So the phase estimate on the time index K should be the one which can maximize this likelihood function. And we can also obtain a closed form expression of this Am's power ML estimate. So after obtaining all of this estimate, we need to derive the Kramer lower bounds to evaluate the estimation performance of the proposed algorithms. So since we know the Kramer lower bounds is obtained from the inverse matrix of the facial information matrix, we can first obtain the Kramer lower bound of this ML frequency offset estimate and this ML constant phase estimate. And then condition on Xi and phi, we can then derive the Bayesian Kramer lower bounds for the linear phase noise, and it can be expressed in this form. So due to the time limitation, I will not mention the details of the derivation of this Bayesian Kramer lower bounds. And similarly, we will obtain the Kramer lower bound for the Am's power phase estimate, which can be expressed as this form. So based on the closed form parameter estimates and their corresponding CILBs. We can then evaluate the estimation performance of the proposed algorithms. So this table shows the simulation parameters, and this figure shows the MSE of the ML frequency offset estimates and the constant phase offset estimates. So you can see that under various phase noise variances. So we can observe that when the SNR is greater than 8 dB, the MSE of the frequency offset and the carrier phase offset both converge to the Kramer lower bounds, which illustrates the accurate estimation performance. But when the SNR is small, it shows some deviations. This is mainly because the phase wrapping phenomenon may exist when the noise effect is severe. And another reason may be that we assume that epsilon t is normally distributed when the SNR is high, but this assumption may not be true at a low SNR. Okay, so well, in the second figure, we investigate the MSE performance of the map estimator of the phase noise with respect to the time index k. So you can see that, and here we consider two kinds of MSEs. The first one is the Gini-aided method. The second one is the MSE-est. So this MSE Gini means that we estimate the MSE by utilizing the theta hat, which is obtained by condition on the actual value of epsilon and actual value of phi. While this MSE-est means that we obtain the theta hat condition on the ML estimate of this Kc and ML estimate of this phi. So you can see that the Gini-aided method actually converge perfectly with our Bayesian-Kramer lower bound. But the MSE-est shows some deviations, especially when n is large. This is because the phase noise is actually somehow the accumulated process. So if there are some estimation errors exist in this Kc and phi, this will lead to the estimation error in our phase noise. And since it is somehow the accumulated process, the error will also accumulate as the k increases. Okay, and we also investigate MSE of the map estimator